Okay, so I'm going to talk about some of the big equations that we use in acceleration. We've already talked about acceleration equals delta v over t, which we could write as acceleration equals v minus v0 over t. But now what we want to do is start bringing in things like the displacement in a problem. Okay, delta x. And to do that, I'm going to do this with an actual graph instead of manipulating equations, just because I think this might be actually a little more helpful. Here's your v0, and let's say an object accelerates up to a certain time, t. Well, if we then look at this, here's the final velocity v, and we know that v equals v0 plus a t. If we want to find out how far something goes, and we have a velocity versus time graph, we do the area under the curve, which would be this area. I'm going to do it a little differently. I'm going to break that into sections. Break that into that chunk and that triangle. And the area of this rectangle is just v0 times t, base times height, v0t. That's the area. So that's the displacement if it just went at v0, if it just cruised along at v0 and it never accelerated. But the fact that it accelerated gives it this extra displacement. And that is going to be 1/2 times the base, which is t, times the height, which is v minus v0. Well, if we look at this equation here, v minus v0 is just going to be at. So when we write the total displacement, it just ends up being v0t, the area of that rectangle, plus 1/2 times t times, again, v minus v0 is just at. And that gives us that final version that some of you may have seen before, v0t plus 1/2 a t squared. I'm going to put a box first around this equation because it's very important, and then around this equation because that ends up being very important. So there's one equation, there's another equation. We've got a third equation that we sort of saw already, which is v average is delta x over t. But if we come back over to this equation, or excuse me, to this graph, if we talk about constant acceleration, the acceleration doesn't change, then the average acceleration over this period will just be kind of the halfway between v0 and v. It ends up being the average of the two accelerations. So we can write, of the two velocities, excuse me. So the average velocity we could write as v0 plus v divided by 2 equals delta x over t. So this is true of an accelerating object. The average velocity equals delta x over t. But we can write that average velocity in terms of v0 and v. I honestly don't use this equation a great deal. Average velocity equals delta x over t I usually use for just constant velocity problems. But, as you see, we can rewrite it so it works for constant acceleration problems. So we have, really, I think of these as the first two equations. If I wanted to see, there's another equation that I think is a little strange. It's also for delta x. If you look at this situation here, you could look at it as this rectangle plus this triangle, or you could look at it as this big rectangle minus that triangle. Does that make sense? So in other words, this shaded area is this whole big rectangle minus that little triangle. Well, that little triangle is also equal to 1/2 times t. Let me rewrite that as 1/2 at squared. When we use this, substitute that into this into this expression. 1/2 at squared. The big rectangle is v times t. So we could also write delta x as vt minus the area of this triangle, 1/2 at squared. That's yet another equation. So we've got 1, 2, 3, 4 equations. And you might notice, I'll go, we need one more equation to really fill this out, and I'll show you why I mean fill this out. And this equation, I'm not going to try to do. You can substitute one of these into another. I believe you substitute this into this, and you can get the result. But it's v final squared equals v0 squared plus 2a delta x. And that's going to be our last equation. I'm going to put a star. You end up using this equation, and this equation quite a lot. These two equations you use less frequently. They're still useful, but honestly you can kind of get away without them. And why do we have 5 equations? Well, we have 5 variables. We have a, delta x, v, v0, and t. And you'll notice you're going to have different combinations. You're going to solve any one of these, you need 3 variables, and you can solve for the fourth variable. So here you have a, v, v0, and t. If you have any 3 of those 4, you can solve the equation. And once you get that 4th, well, you can use any other equation to get the 5th. But you'll notice this one doesn't have a delta x in it. This one doesn't have a in it. This one doesn't have v final. This one doesn't have v initial, and this one doesn't have time. So they all serve different purposes because you use them in different situations depending on what variables you have there. Okay, let's do a problem. Let's say I roll a ball up a ramp. It leaves my hand going 4 meters per second. Acceleration down ramp is 2 meters per second squared, and we want to say where is it after 6 seconds. Okay, that's supposed to be where. There we are. I've got to draw a picture. I want the solve method. Sketch, objective, list variables, and find and solve equations. I'm going to call up positive. Some people always make the positive direction the direction of the acceleration if they know it. I am not that person. So I am just going to make up positive. And I'm sorry, I want to adjust this so I get a little more in the field of view here. There we go. Okay, I'm going to call up positive. Solve method, sketch. Objective is where is it? I'm going to call that delta x. I've got v0, which is positive 4 meters per second, because positive is upward and the velocity is in the upward direction. Acceleration is down the ramp, negative 2 meters per second squared, and time is 6 seconds. Well, what I want to do is I want to find out what equation relates these 4 variables. Delta x, v0, at. It so happens, if I look at this, there's no delta x. That won't help. There's a delta x, but we don't have v final. You come down here, I'm looking for delta x. I have v0, I have t, I have a, I have t. So we write down our equation, v0t plus 1/2 a t squared. We write delta x and we substitute our variables in. 4 for v0, t is 6. I'm going to leave out the units so it doesn't look too crowded. Everything's in comfortable units, KMS units, so it will come out. I could demonstrate that, but I just don't want to get lost in that right now. This is 24 plus 36, but negative 36. And this ends up being negative 12 meters is my delta x. Okay? Now notice, I asked where is it? I could have asked how fast is it going? If I did that, we'd be looking for v. And we'd be using different equations. Now, if I started out asking that, v0, a, t, and v, I would have to use this equation. And let's do that. A equals v minus v0 over t. Negative 2 equals, I apologize, it looks like I'm going off the end, v minus 4 over 6. And when you solve that, you get negative 12, negative 8 equals v, negative 8 meters per second. I used this equation, a equals v minus v0 over t, but I could have used any equation that had v in it, because I have 4 variables after I'd solved this. So v0, a, t, and delta x, I could have used this one. I'm looking for v, I have v0, I have a, I have delta x. Sometimes you're going to come up with a situation where you've got 3 variables, and a lot of people will just memorize those starred equations. And what you can do, v0, a, and t, well, here I can solve this, but you'll sometimes have an equation, a situation where you don't have the equation to solve that, but maybe you have the variables that will help you use one of these equations to solve a different variable. Then you can use that new variable into one of the other equations and solve what you're looking for. I'm going to do one more problem, and this one will be, I have to think about this one. I'm going to say I throw a ball up. I'll talk about free fall later, but I throw a ball up, throw a ball up at 40 meters per second. And I want to say, where is it? That's a delta x question. When velocity is, let's say, 20 meters per second down. And something I need to tell you is the acceleration due to gravity for an object in free fall when there are no forces other than gravity is, I'm going to round it to 10 meters per second squared down. And in AP you can use 10. The actual number is 9.81 meters per second squared down. We'll talk about that in the next video. You end up using free fall an awful lot in acceleration problems just because it's such a handy acceleration that people know. So now I'm going to call up positive just because that's who I am. I'm looking for delta x. Frequently you'd write delta y when you're talking about vertical. I'm just going to leave it like this because these are the equations we've used. We wrote delta x. V0 is 40 up, which is positive. V final is 20 down, which is negative. And the acceleration is 10 meters per second squared down, which is negative. And if I go through all my equations, what I eventually find out is that the equation that helps me the most is v squared equals v0 squared plus 2a delta x. Negative 20 squared equals 40 squared plus 2 times negative 10 is the acceleration times delta x. And so I end up with 400 equals 1600 minus 20 delta x. 400 minus 1600 is negative 1200 equals negative 20 delta x. Divide by 20 and you get 60 meters is delta x. That's pretty far up there. So that's how you use these big equations, selecting them and using them, applying them with your listed variables and your objective. Most important thing I'd say is picking a frame of reference. That sketch. It doesn't have to be a beautiful thing. You'll notice I didn't even have a ball written there. Sometimes you'll have more complex problems where you have two objects moving, a car catching up with another car. Well, at that point, what you want to say is, let's say when something catches up, you might want to say both of their displacements are the same. So you'd write one equation for the displacement of one object, another expression for the displacement of another object, and you'd set those two expressions equal. I may do a more complicated problem video later on, but that's the basic approach. So these end up being 5 really useful equations, and if you just apply them using the solve method, you're going to be in great shape.